Hi there, my name's Parth and it's great to be back. I haven't uploaded a video in a while and that's been for a couple of different reasons. I'd like to take some time to chat about those reasons for a moment, but if you want to skip to the real main parts of this video, the real juicy stuff, then head over to this timestamp here. Okay, so why haven't I uploaded in over a month at this point? Well, firstly, I realized that I needed to spend some time learning physics again, in order to make sure that I can make some decent videos on this channel. I'm still in the middle of doing that right now as we speak actually. But secondly, I've been really enjoying working on a few different projects over the end of 2022 and beginning of 2023. For one, I've been creating and uploading a load of music, which has been a heck of a lot of fun. Please do check it out over on my second channel. It's called Parth Music. And let me know what you think. I'd really appreciate your support on there. On top of all the music stuff, I decided to take my passion for sports, specifically cricket, and channel that into something also very fun. Together with a friend of mine, I've started up a page on YouTube, TikTok, and Instagram called Cricket in a Minute. Over there, we discuss various interesting things about cricket, such as terminology, tactics, and amazing players in short 1-minute videos. So if you're a cricket fan or just want to know more about the sport, then head over there too. That's Cricket in a Minute. Another thing I've been doing over the past couple of months is preparing a talk. I was very kindly asked to head over to Reading School and explain a physics topic to students who were in their first year of doing A-level physics. I was really excited by this opportunity, but also super nervous. I haven't done much public speaking in a long time, and I was also unsure if I could translate well the stuff I do here on YouTube to real life. I decided to discuss the premise that the universe as we know it exists because of identical particles. Super interesting idea in my opinion, and I had great fun pitching the talk at a level that I felt confident explaining without delving too deeply into the intricacies of the maths and without getting bogged down in details that are ultimately important but not super useful for just getting the feel of a concept for the first time that you hear it. So this video is a recording of that talk. Now, I should mention that my camera decided to do some weird stuff halfway through, but you can still see the slides and hear me talking, so hopefully all of the talk can be followed relatively well. And also, like I said, I was super nervous doing this talk, but the students were wonderful and they asked me some really insightful and interesting questions. So here's the talk. I hope you enjoy it. Thanks very much. Hi everyone, yeah, nice to meet you. I'm Parth G. As we said, we're going to be talking about this particular title here. Just to let you know about myself, I'm a science educator. I did a degree, as Dr. Lewis Brown said, at the University of Cambridge, and I like making YouTube videos. This is my YouTube channel. It's called Parth G. Very easy to search up after this talk, so if you want to learn more about physics, go over there. And there's two things I want you guys to know about this talk before we get into it. The first is that we'll be looking at some complicated looking maths. So it's not actually that difficult to do, but it just looks complicated. It's the concepts that are more difficult, especially when we're talking about quantum physics. But we'll be going through them step by step, and hopefully you guys will be able to keep up. And if there's any questions, we'll have some time towards the end as well. The other thing is, obviously you can see this talk is being filmed. It's not pointed at you guys. If this talk goes well, you'll see it up on my YouTube channel. If it doesn't go well, you won't see it up there. So the premise is that the universe exists because of identical particles. What are we talking about? The very first thing, we'll start with atoms. So I need some audience participation here, guys. Let's help me out here. What particles make up atoms? Yep. That's true. Quarks do make up. That's fair point. Are electrons made of quarks, though? No, that's true. So what about think slightly bigger? Anything? Any other particles? Yep. Yeah. Neutrons is a good example. Quarks we'll keep that in mind, actually. Right at the back. Protons, yep. What else? Yep. There you go. We've got protons, neutrons, and electrons. And yes, you are absolutely right. The protons and neutrons are made up of quarks. We'll be looking at that in a moment as well. The interesting thing here, though, is that electrons are arranged in shells, right? We know that the inner shell has 2 electrons in it. We know that the next shell out can have up to 8 electrons in it. And we'll be looking at why that's the case. I just want to check, has anyone heard of orbitals? Yep, you guys all know about orbitals, fantastic. Okay, great. So we know that each shell has orbitals in it, and each orbital can hold 2 electrons in it. So the first shell has 1 orbital, 2 electrons. The second shell has 4 orbitals, can hold up to 8 electrons. We'll be looking at why that's the case. To do that, we'll talk about quantum physics. So a little bit of a leap here from atoms all the way to quantum physics. What does anyone in the audience know about quantum physics? Any ideas? Go for it.
It's physics of particles that are atom-sized or smaller,
Perfect. Yep. 100%. That's really good. What else? God, you guys are so good. Heisenberg's uncertainty principle coming in as well. Really nice. What else? Any of your thoughts? Yeah, go for it. Yeah, you listen, you guys should be doing this talk instead of me. That's exactly what I was going to say. The thing that we really want to know about quantum physics today is that it's a study of small objects, right? Atoms and smaller, as you said, so the particles that make up atoms, and even smaller particles than that, so like quarks, as you mentioned earlier. The other thing is, even though quantum mechanics is basically just a bunch of maths that allows us to predict how these small particles will behave, we've got a lot of evidence that it's a good theory. And what I mean by that is quantum mechanics, the maths, makes predictions about how electrons, protons, neutrons, quarks should behave, and then we test it. And there's a huge bunch of evidence at the moment that suggests that quantum mechanics does indeed predict the universe in a pretty reasonable way. Here's the thing though, if we're studying a particle, right, in classical physics, or the physics that we study at GCSE and A-level, if we're studying a particle, what are some of the things we might want to know about it in order to study its behavior? Any examples? Yep. Yep, that's really good. Yep, velocity as well. Yep. Spin, yep. Yeah, cool. Yeah, I've got a few examples here. Position, speed. I've drawn a little speed camera because I didn't really know how to demonstrate speed for a particle. And it took me ages, so please appreciate that. And mass as well. These are three examples. The problem is, though, when we come down to the quantum scale, when we're looking at particles that are really, really small, we aren't able to deal with position and speed especially very easily. When we measure a particle's position, we find out where it is, but then if we look away and we try and measure it again, there's a small chance that it's very far away, or there's a very small chance that it's completely on the other side of the universe. We're most likely to find it exactly where it was before, or roughly in that region of space, but there is a small chance, like I say, that the position doesn't really make sense to us. It doesn't follow common sense, or it doesn't follow the laws of, Newton's laws of motion or classical physics. So instead, we work with a quantity that's a little bit smoother changing. It's called the wave function. Wave function is just this mathematical function, just like y is equal to sine x or y is equal to, x squared, whatever they may be, they're mathematical functions. A wave function basically relates to the particle and tells us some information about, in this case, the particle's position, right? So I've drawn position on the x-axis, and I haven't labeled the vertical axis properly. In this case, I have. But here's the point, right? The wave function gives us information about the particle's position. How does it do that? Well, as we can see here, here's a simplified diagram of a wave function. We need to take our wave function, we need to square it. Once we square this wave function, we get this purple curve, which I've drawn slightly taller because obviously we've squared every single value of the wave function at every point. And this square, what does it represent? Yeah, go for it. Very nice. There we go, we've got probability. So what this basically is telling us is psi squared. By the way, this is the Greek letter psi, the trident-looking thing. That's what we used to represent wave function. And the purple thing is the probability distribution. So we've got a peak round about the middle. What that means is that we're much more likely to find our particle in the middle when we search for a particle than we are to find it around the sides. That's basically all the wave function tells us. So to recap, we have this wave function that changes nicely and smoothly, so we're able to work with it. We square it, and that gives us the probability of finding our particle wherever we're looking for it. In other words, we don't necessarily deal directly in quantum mechanics with position, with speed, and so on. We deal with a wave function first, and that gives us information about position, speed, etc. So, this is just demonstrating that we're more likely to find it middle, less likely to find it around the sides. So the question is then, why do we care about the wave function? If the wave function isn't directly giving us information, if it's the square of the wave function that gives us information, then why do we care about it? Well, this is why. The wave function has some amount of information in it that would be lost if we just worked with the squared values. For example, if we took off all of quantum mechanics, squared everything, got rid of the wave function, and just worked with the purple thing, there would be some information that would be missing. For example, if one wave function corresponding to like an electron looks like that on the left, And if another one looks like that on the right, all the exact same values, but they're all negative rather than positive, squaring them actually gives us the same purple function, the same probability distribution, right? So the point is that we would lose information if we didn't work with a wave function. But then the question is, again, why do we care? The thing that we can directly measure is the probability distribution. We can actually measure where the particle is, and that tells us how likely we are to measure the particle again and again if we tried to do the same experiment over and over again. So why do we care that there's some information missing here? We'll look at that in a second, but just to give you a bit more of an example, if you take a positive value, you square it, and if you take a negative value that's the same magnitude, but you square it once again, you get the same probability distribution. I'm going to pause here for a second. Any questions so far? Yep. Really good question. So the only reason we talked about linear scale so far is because that's an easy one to draw. But you can actually have a wave function that's not so easy to draw that gives you the probability of finding a particle in 3 dimensions. You would just need x, y, z, and a 4th axis to represent the probability, which is why I haven't drawn it. I don't know how to draw in 4D. But yeah, you're right. This is a really good question. Okay, so we've talked about single particles so far. We saw how the wave function, when we squared it, gave us the probability of finding the particle at different points in space. But what about if we're dealing with multiple particles? Let's say we've got 2 particles, maybe they're 2 electrons, or we've got a proton and an electron. Doesn't matter what they are for now. We might think that 2 particles each have their own wave function. But when we're dealing collectively with a system, actually we've only got one wave function that describes the whole system. Here's how we would calculate probabilities for finding, for example, particle A at x is equal to 1, and particle B at x is equal to 4. We take our wave function, whatever that is, we'd stick in A on the left, and we'd stick in B on the right. We'd do some math that includes information about x is equal to 1 and x is equal to 4, and we'd spit out a probability. What that probability is telling us is how likely we are to find particle A here and particle B here. So now I have a question for you guys. How would we write the probability of having these particles found in the exact same positions, but swapped around? Yep. Equals negative psi squared. Okay, so why have we got negative psi? That's later. So we actually, what I want to know is, you're predicting my talk, this is really good. So what I want to know for now is how do we write the probability of finding these 2 particles the other way around? If this is the probability of finding the particles this way around, then how do we write them swapped around? Yep. Perfect. That's what I'm looking for. Yep, there you go. So instead of AB, we write BA. We do some amount of maths. We'll come to your point in a second. But this is the probability of finding the same particles, but swapped around. We're going to be thinking about this swapping around quite a lot in this talk, okay? So keep that in mind. We want to think about what happens when we take 2 particles and we're able to swap them around. Let's consider, for example, if we have 2 particles that are exactly the same as each other, and when we take these particles and we swap them, we're exactly equally likely to find them this way around as we are to find them this way around. The first point I want to make, so we've got these 2 particles. The first point I want to make is that this isn't necessarily always the case. For example, if we have 2 different particles, A is shinier than B, or A is more blue than B. Let's say A is a proton and B is an electron. And we just happen to have loads and loads of negative charges closer to the left-hand side. Then we're much more likely to find the proton close to the negative charges than we are to find the electron close to the negative charges, right? Because opposite charges attract and like charges repel. So it isn't necessarily true that the probability of finding particles this way around is the same as the probability of finding them this way around in the same positions. Except for when we're dealing with particles that are identical to each other, such as 2 electrons, 2 protons, for example, right? In that case, the probability of finding particles this way around is the same as the probability of finding particles this way around, and crucially, that's true for any possible positions that the particles could be in. So here and here, same probability. Here and here, same probability. Here and here, same probability as each other. If that's the case, if we have particles like that, they are known as indistinguishable particles. Anybody know what indistinguishable particles are? Yeah? Yeah, exactly. So not only are they identical to each other, they have the same mass as each other, same charge as each other, but we physically cannot tell which is which. When we've got two particles, we know that they're there. We look away, we look back again, we don't know which one was which anymore. The interesting thing, though, is when we try and do some maths, pretending that we know how to tell them apart. So we label them particle A and particle B, and we see what happens if we were to swap them around. What I'm really interested in now is what happens to the wave function when we've got these indistinguishable particles. So as you mentioned earlier, this is what we're coming on to. What happens when we've got particles? What happens to the wave function when we've got these indistinguishable particles? We know the probability stays the same, but what happens to the wave function, which is the square root of probability? So we're taking square roots. Any ideas what kind of solutions we get? You mentioned one of them, actually. Do you want to say it again? Psi of AB equals negative psi of BA. That's really good. Yep. Spot on. Yeah. Yeah, exactly. I mean, yeah, I'm really happy you guys are remembering your negatives. I would always forget. Actually, there's only two that we're really interested in, because if you think about it, two of those combinations are equivalent to two of the others. So plus one is the interesting one, and 1 is plus, 1 is minus is the interesting one. Here's what I'm talking about. In one case, the wave function when the particles are this way around is exactly the same as the wave function when the particles are swapped around. So the wave function doesn't change either. Neither does the probability, because they're indistinguishable particles. If that's the case, the particles that we're talking about are called bosons. Anyone got an example of a boson? Yep. Very nice. Anyone know the most popular one, I guess? Yep. Yeah, you. Yep, that's a good example as well. Yep. Yep. Yep, more. And gluon, there you go. These are examples of bosons which we're not focusing on today. Instead, what we're focusing on are fermions. This is the other kind of behavior that you can get, where if you take a system of particles, of two particles, and you swap them around, the wave function becomes negative of what it was before, even though the probability is staying the same, because the square of those stays the same, right? What's an example of a fermion? Yep. Yeah, that's the one we'll be focusing on today. In fact, I've got a whole slide that says electrons are fermions. We've got two electrons there. When we swap them around, the wave function becomes negative of what it was before. Why do we care? This is my question. Every time I'm asking, why do we care? Because if the only thing that we can really measure is psi squared, the probability, then why do we care that the wave function becomes negative of what it was before? We can't directly measure this. Well, as it turns out, this minus sign over there has some really important consequences indirectly. I would go as far as to say that this minus sign is the reason that the universe exists the way that we know it. To understand what I mean by that, we need to take a closer look at the wave function. When we're dealing with electrons, let's talk about specifically electrons as we have been doing for the past slide, their wave function has two parts to it. Remember we said that the wave function contains information about our system. Right? So before we saw how it told us about the position of our particles. When we're dealing with electrons and atoms, there's two parts to it, the orbital part and the spin part. That's the really fun stuff. Let's talk about the orbital part first, though. Basically, the orbital part just tells us which orbital the electron is in. So if it's in the first shell, there's only one possible orbital it could be in. It's in the 1s orbital. The s orbital is the only one that exists in the one shell. In the 2 shell, or the second shell, there's one s orbital and there's 3 p orbitals. So for any of these electrons, we could just say that theta, the orbital part, is equal to 1s, for example, or 2s if it's in the second shell and the s orbital. The spin part is a bit more interesting. Anybody know what spin is? You go with you? Yeah.
Kind of like angular momentum.
Yeah, pretty much. Yeah, exactly. So spin is, for all intents and purposes, just another property that electrons can have, just like charge, just like mass, but it has some interesting behaviors. Every single electron has the same amount of spin. This is what contributes to it still being indistinguishable from each other, but those spins can point in different directions. With electrons, we're allowed to have spins that point in 2 directions. We call them spin up and spin down. Really, the names don't matter, it's just a name. But we need to know what's most important here is that there are two possible spin states, spin up and spin down. Now, if we really wanted to talk about spin in great detail, as you mentioned, it's angular momentum, but do we have time to talk about it properly and what it actually represents? Lol, no. We don't have time to talk about that, but what I want to look at now is this particular scenario. Now that we know about the orbital part and the spin part, what does the wave function of something like this look? At the top, we've got the possible orbital states. I've drawn 1s and 2s just to keep things simple. And we've got two electrons, both with the same spin. Let's say they both spin up. Let's construct the wave function. We know the wave function for particles A and B must be equal to the orbital part, which for particle A is 1s, and for particle B is 1s as well. And then we multiply this by the spin part. We know that particle A is spin up, and particle B is spin up as well. What happens when we take these two particles and swap them around? What does the wave function look like?
Well, on the left-hand side, you have negative side B, A. On the right-hand side, you have the exact same thing, which is only possible if it's 0.
Exactly. We want to find that the wave function becomes negative, right? This is what we said earlier. We're working with fermions. We're working with particles whose wave function becomes the opposite of what it was before. So, what happens when we swap them around? Well, we know that particle B comes first now, and particle A comes second. But both of these particles are in the 1s state. So we get 1s, 1s, and for the spin states, because they both spin up, we still get up and up. The thing to notice here is that the wave function on the right-hand side looks the same as it did before we swapped the particles, and that is not allowed. We're not allowed to have this for fermions. What this is telling us is that we can't have two electrons with the same spin in the same orbital. However, let's check what happens when we have two electrons with opposite spins in the same orbital. This time we've got spin up for A, spin down for B. Once again, we construct the wave function. We've got 1s, 1s for particle A, particle B, and we've got spin up and spin down this time, which means that when we take the particles and we swap them around, we get a wave function that looks a bit different. The orbital part looks the same, but the spin part now says down and up. Now, I've simplified the spin mathematics a little bit here, but really, what you should take away from this is that the maths of quantum mechanics, at least notation-wise, looks exactly like this. So if you were to look into a research paper or a textbook, this is the kind of stuff you'd be seeing. And hence, when you go home today, you can say that you did some advanced quantum mechanics. So here's the thing. The spin part of the wave function looks different when we swap it. And the maths works out that the wave function does actually become negative of what it was before. This could feasibly be allowed. Whereas in the previous case, we saw that that absolutely cannot happen because the wave function looks exactly the same as before. That's not allowed. So what we're learning here, we'll come to that slide in a minute. What we're learning here is that we're allowed to have two electrons in an orbital with opposite spins, but we're not allowed to have two electrons in an orbital with the same spin. I want to recap that very quickly. We started with two electrons. We swapped their positions. We saw that their probabilities must be the same because they're indistinguishable particles. So finding them in this orientation is the same probability as finding them in this orientation, regardless of where we're finding them. However, we saw that for fermions, the actual wave function itself becomes negative when we swap their positions. And so we saw that two particles with opposite spins are indeed allowed in a particular orbital, but two particles with the same spin are not allowed. So the first thing we talked about was atoms. We saw that electrons were organized in orbitals. We saw that electrons, therefore, were arranged into shells because each shell has a certain number of orbitals, and each orbital can only hold two electrons. To figure out why, we turned to quantum mechanics. We saw that quantum mechanics deals with wave functions, and we saw how the square of the wave function leads to probabilities. Then we saw that for multi-particle systems, the probabilities can be affected when we swap the particles around, this orientation versus this orientation. But for indistinguishable particles, the probability stays the same. We can't tell which one is which. We saw specifically for fermions, such as electrons, that the wave function becomes negative of what it was before. And that led to us realizing that we can't have more than one fermion, or more than two fermions in a particular orbital, and they always have to have opposite spins. This is the reason why Electrons are arranged in orbitals the way that they are in atoms, and therefore the atomic structure looks the way it does. The atomic structure is what contributes to things like chemical bonding, ionic bonding, and covalent bonding. And that is what allows the universe around us to look like the way that it does. We've got solids, liquids, and gases. We've got things that bond in many different ways. We've got semiconductors, and so on and so forth. All of that has to do with the electronic arrangement of atoms. Cheers.